In this video, we are going to learn how to find if a given vector field is conservative, and if it is conservative, then how to find potential function. So let's say f is given by mi plus nj and pk. So m and p are its component functions. F is conservative field if and only if its component function m and p satisfy these three equations. Here we are taking partial derivatives of the components, and they must be equal to the partial derivative of some other component with respect to some other variable, right? So it's conservative if these conditions are satisfied, and if these conditions are satisfied, then f is conservative. So it's an if and only if condition. So let's say the function f is conservative. What happens then? That means there exists a function small f such that this vector field f is gradient of this function f. Now what is gradient of f? It's fxi plus fij plus fck. So if we compare this with the given equation for the vector field, given expression for vector field, what do we get? If f is a conservative field, then its component functions m and p are given by partial derivatives of this potential function with respect to x, y, and z. Alright, so let's work on an example. We are given the vector field f here. Now we want to check if it's conservative field or not. So what do? We check if these three equations are satisfied. So first, let's write down the component function of f. M is equal to this, n is this function, and p is equal to this. So let's find out the partial derivatives of this component function m, n, and p. So derivative of m with respect to y is this function. Derivative of n with respect to x is this function, and they are equal. Now let's move on to the second equation. Partial derivative of m with respect to z is 0 because there are no z variable in m. Similarly, partial derivative of p with respect to x is 0 because there is no x variable in p. So both of them are 0. So the second equation is satisfied. And now the third one, partial derivative of n with respect to z turns out to be equal to this, and partial derivative of p with respect to y turns out to be equal to this. So they are both equal except some of the terms have been rearranged, but they are equal. So the third condition is also satisfied. So the component function of the vector field f satisfy all these three equations. So that means the vector field f is conservative field. So that means there exists a function f such that capital F is gradient of this function. Alright, so let's understand what that means. So the vector field f is given by gradient of f, which is equal to fxi plus fij plus fck. Now we already know the values of m, n, and p from the given value of the vector field, right? So what does that mean? That means we know the partial derivative of this potential function f with respect to x, y, and z. They are equal to m, n, and p respectively, right? So now we have the partial derivative of the potential function. So how do we find the potential function? We already know derivative of a function with respect to x. So what can we do? We can integrate this function with respect to x by treating y and z variables as constant. All right, we are integrating with respect to x, so any other variable will be treated as a constant. So what do we get after we integrate this equation with respect to x? We get this function where g is a constant of integration. Why is this function of y and z? Because we treated y and z as constant when we integrate with respect to x. Now if we can find this function, we can substitute its value here and we will have the candidate for the potential function. So how do we do that? How do we solve for g? So let's take derivative of this potential function f with respect to y, right? So there is no y here, there is y here, so its derivative is secant square x plus y, and then we have the partial derivative of g with respect to y. Now we already have an expression for partial derivative of the potential function f with respect to y, it's equal to n, right? So we already have one function which is equal to fy. Now these two must be equal. So we set them equal to each other, and these first term will cancel out, and that leaves us with the partial derivative of g with respect to y equal to y plus square root of y square plus c square. Okay, so now we have the partial derivative of g with respect to y equal to this function. Now we integrate this function partial derivative of g with respect to y with respect to y, and we treat z as a constant. So what happens after that? After integrating, we get g is equal to integral of this function with respect to y plus this function h of z, which is a constant of integration. It's function of c because we treated z as a constant, right? So let's integrate this function here. We rewrote this expression as like we divided by 2, we multiplied by 2. Now this is of the form, this integral is of the form integral of a function f raised to power n multiplied with derivative of this function f. Now what's our formula for integral of such a function? Integral of derivative of f, first derivative of f multiplied with f raised to power n is f raised to power n plus 1 divided by n plus 1. So in this case, the power of the function f is negative 1 by 2. So we use this formula and we find out that integral is equal to this. We cancel out the half and we have the expression for the function g. G is equal to square root of y square plus c square plus h of c, where h is a function of one variable z. Now we already have this expression f is equal to this function plus g, right? And we calculated that g is equal to this function, where we know we want to find out just h of c, and once we know this function, we'll have an expression for a potential function. So let's substitute this expression for g in the equation 6. So f turns out to be equal to this function. So we don't know what is h of c, so for that, to find that, we take derivative of this function with respect to z, okay, which is equal to this. And now look at this equation. The derivative of potential function with respect to z is equal to the third component p of the given vector field f. So we already have one expression for fc. So these two must be equal. So this derivative of f with respect to z must be equal to this function. So we set them equal to each other and we get that derivative of this function h with respect to z equal to 0. That means h is a constant function, right? So we substitute this value back in this equation here and we have a candidate for the potential function. So the given vector field f is gradient of this potential function f given by this expression here. Now the important thing to notice here is that we know that work done by a conservative force is given by this expression, right? And it's independent of path. Now why is that independent of path? Now we know it because a conservative field is gradient of a function f called potential function. So when we substitute conservative field f equal to gradient of f in this equation here, in this integral, what do we get? We are going to get the potential function integral of gradient of the potential function, which will be f evaluated at the limit points. Okay, so that means work done by conservative force is independent of the path, or if f is a conservative field, we can calculate its integral just by substituting the value of the limit points in the potential function and subtracting them.